morning, students. Myself, Vijay Shankar from Electronics and Communication Engineering Department, Chevrolet Engineering College. Today, we are going to discuss about the Fourier transformation examples. We already seen. So, what is a Fourier transformation, and what are the properties of the Fourier transformation, and some of the examples in the Fourier transformation also. That is the Fourier transformation of the exponentially decaying function. Exponentially decaying function. The e power minus at mu of t. E power minus at mu of t. The Fourier transformation is 1 by a plus j omega in angular frequency, or otherwise 1 by a plus j 2 pi f in the normal frequency. Now coming to the next one, the Fourier transformation of the impulse function. Fourier transformation of impulse function. We already know the impulse function, the integral minus infinite to infinite delta of t dt is equal to 1 when t is equal to 0. Integral minus infinite to infinite, the delta of t, the impulse function, dt is equal to 1 for t is equal to 0, and 0 for t not equal to 0. T not equal to 0. This is an equation, the functional representation of the impulse function. How to find out the Fourier transformation of this impulse function. So the graphical representation showing that from minus t to the t, only we have at t is equal to 0, the magnitude is 1. It looks like the same in the discrete time and the continuous time. So according to the definition of by the definition of Fourier transformation, x of f is equal to integral minus infinite to infinite x of t e power minus j 2 pi f t into dt. Otherwise, in terms of angular frequency, the x of omega is equal to integral minus infinite to infinite x of t e power minus j omega t dt. What is the x of t here? The delta of t. Integral minus infinite to infinite. Integral minus infinite to infinite. The x of t is a delta. The impulse function e power minus j omega t dt. And we have only the delta of t at t is equal to 0 only. The remaining all the terms from minus infinite to less than the 0 is a 0, and greater than the 0 up to the infinite value, the impulse function is a 0. The shifting property of the impulse function is given as shifting property of the impulse function. See here the integral minus infinite to infinite f of t delta of t minus t naught. Delta of t minus t naught is equal to f of t naught. Why means the signal f of t having the sample at t naught, delta is shifted to t naught means the value at the t naught only we have the output function for the given signal of f of t when combining with the delta function, the shifted version. Okay, so let us, I will explain how you get integral minus infinite to infinite f of t delta of t minus t naught is equal to f of t naught. That f of t naught, f of t is equal to having the values, it is 0. Let us assume the 1 value. Okay, and at minus 1, 2, and 1, let it is a 0.5. Okay, this is a signal f of t given. The another signal I'm taking as a delta function, delta of t, at t is equal to 0, the value is 1. Now I'm shifting the sample delta of t minus 1. Delta of t minus 1 means one sample is shifted towards the right side because it is a delay function at 0, 0 value. Now at 1, the sample is get at the 1. Okay. Now you can combine these two functions as of integral minus infinite to infinite f of t delta of t minus 1, delta of t minus 1 dt. Simply the multiplication factor. See the minus 1 here, the minus 1 is a 0, and 1 and the 0, it is a 0. But here at 1, f of t is a 0.5 and delta of t minus 1 is a 1. Okay, finally it is equal to f of 1. Why? It having the 1, the 0.5, and here it is a 1 into 0.5, f of 1. So the function is also the same, delta of t minus t naught. It is a t naught means, that is a t naught. The function f of t is a t naught. Follow my dear students. The integral minus infinite to infinite f of t delta of t minus t naught. So in this range, we have only the values of minus 1, 0, and 1. When the product minus 1 into 0 here, it is a 0 value, and 0, not the 0, at t is equal to 0, f of t is 1, at t is equal to 0, that shifted delta function is a 0. So these two product is a 0. So finally we'll get the delta function is shifted with the t naught samples, nothing but it is a 1 into 0.5. Means how many samples it is shifted, that sample only will get that sample, not the samples, my student, that sample only you get f of t naught, f of t naught. Understood? Suppose the t naught is equal to 2 means f of 2. If t naught is equal to minus 1, f of minus 1. Any function or any signal is multiplied with the delta function, we'll get the same function, f of t. If suppose the integral minus infinite to infinite, f of t delta of t dt, delta of t dt is equal to f of t only. F of t. If it is shifted with the t naught samples, that f of t signal becomes f of t naught. Understood, my dear students? I got the idea how we got the integral minus infinite to infinite f of t delta of t minus t naught is equal to f of t naught. Using this shifting property of the impulse function is given f of t naught. Here f of t is equal to, you see in these two functions, I'm taking the x of t as a delta and e power minus j 2 pi f into t is f of t. So x of f is equal to integral minus infinite to infinite e power minus j omega t as f of t here at t is equal to 0, and delta function here, the delta of t minus 0. T minus 0 is at delta t only, dt. Understood? Is equal to e power is a value at t is equal to 0, value 1, e power minus j omega What is a t here? T is equal to 0. This is at t is equal to 0. At t is equal to 0, the delta t minus 0 is a value 1, and I substituted the t is equal to 0 here. In all this minus infinity, infinite, we have only one value at t is equal to 0 because the delta t is 1 for t is equal to 0. So anything power 0 value is 1. Therefore, the delta of t, the Fourier transformation, is 1. Okay, my dear students. So f of t is, I am taking the e power minus j 2 pi f into t at t is equal to 0. Integral minus infinity, infinity, e power minus j 2 pi f into t, delta of t minus 0 into t. Using this equation is f of t and delta of t minus 0, f of t naught. F of t naught. So f of t naught is a 0 here. F of 0 is equal to e power minus j f, e power minus j is also there, my dear students. So e power minus j 2 pi f into 0. Anything power 0, the value is a 1. The Fourier transformation of impulse function is 1. Now, how we can find the amplitude spectrum and the phase spectrum? So everything is the same here. The amplitude spectrum always 1 from minus t to the t, because the delta of t is equal to 1. The amplitude, the 1 from all the values, shows the amplitude spectrum of the delta function. It shows the delta function or unit impulse contains all the frequencies with the same amplitude. All the frequencies with the same amplitude in its spectrum. Okay. So we learn two functions. The Fourier transformation of e power minus at mu of t. The Fourier transformation is 1 by a plus j omega. And now we learn the Fourier transformation of the delta of t is 1. These are the standard signals, my dear students. Exponential signal and impulse signal or delta impulse signal. Okay. I go for the next one. The periodic function. See, we already seen this, the Fourier transformation of a periodic function. Now, another example, find the Fourier transformation of the signum function. Find the Fourier transformation of the signum function. We already know the signum function is equal to signum function, signum of t is equal to -1 for t is greater than 0, 1 for t is less than 0. Okay. Or in step function, the signum of t, 2 mu of t minus 1. 2 mu of t minus 1. Okay. Now I have to find out the Fourier transformation of the signum function. See, minus, not the -1, my dear students. So here it is a plus and this one is a minus. For positive values of t, magnitude is 1. For negative values of t, x of t, the signal is a -1. Here, e power minus a magnitude of t I am taking. E power minus a magnitude of t, the signum signum of t is equal to signum of t. Or otherwise, directly you can find out the signum of function of the Fourier transformation after finding out of the mu of t. You can find the Fourier transformation of the step function, and directly you will get the signum function. First of all, you can see the Fourier transformation of the step function. Then you go for the Fourier transformation of the signum function, my students. First of all, you can see that so what is the Fourier transformation of the step function? I will explain here. Now you got the signum function, signum of t is equal to, saying that it is a +1 for t is greater than 0 and -1 for t is less than 0. Okay. Or otherwise, the signum of t is equal to 2 into mu of t minus 1. How it is the step function showing that mu of t is equal to 1, but t is greater than or equal to 0. Then the signum function. Now you got the signum function. Signum of t is 2 into mu of t minus 1. Mu of t for the positive values of the t. For positive values of t, here the value is 1. So 2 into 1 minus 1. 2 into 1 minus 1. At t is greater than the 0, the mu of t is 1. So 2 into 1, 2. 2 minus 1 is the 1. Magnitude is a 1, my students. For negative values of t, the values is a 0. So 2 into 0 minus 1. 2 into 0 minus 1. Like that, we will get the characteristics of the signum function. Now, to find out the Fourier transformation of the signum function, first of all, you can find the Fourier transformation of the mu of t. Fourier transformation of the mu of x of omega is equal to integral minus infinite to infinite x of t. According to the definition of the step function, not step function, Fourier transformation e power minus j omega t dt. Okay, my dear students. And that is equal to integral minus infinite to infinite x of t is a mu of t e power minus j omega t dt. That is equal to, it's a Fourier transformation of unit step, my dear students. Unit step. What is a unit step function? Saying the functional representation, mu of t is 1 for t is greater than or equal to 0. And remaining minus infinite to the less than the 0, the value is 1, 0. So I'm changing the limitations here. 0 to infinite. Mu of t, the value is 1. E power minus j omega t dt. Okay, my dear students, is equal to 1. So integral e power minus j omega t, e power minus j omega t by minus j omega from the limits 0 to infinite. That is equal to e power, I'm applying the upper limit minus j omega t as infinite minus e power minus j omega into 0 whole divided by minus j omega. Okay, my dear students. Anything power infinite is a 0. Anything power 0 is a 1 by minus j omega. Okay. Then, so minus and minus get cancelled. The Fourier transformation of a unit step function is 1 by j omega, my dear students. D of t. The Fourier transformation of d of t is 1 by j omega. So directly we can find out the Fourier transformation of the step function. Okay. Okay, my dear students. Then you go for find of the signum function. Here it is multiplied with e power minus a, the magnitude of t. E power minus a, magnitude of t. So first of all, you can find out the e power minus a and the magnitude of t, the Fourier transformation also. E power minus a, the magnitude of t, the Fourier transformation. How you can find the e power minus a t, the Fourier transformation? So again, you can take by the definition of Fourier transformation. X of omega is equal to integral minus infinite to infinite x of t e power minus j omega t dt. E power minus j omega t dt. Now I can substitute the e power x of t, the value is e power minus a integral minus infinite to infinite x of t. What is x of t? Now I am taking this function e power minus a, the magnitude of t. E power minus a, magnitude of t into e power minus j omega t dt. Okay, my dear students. So actually, and this function, if I am assuming the e power minus a t, e power minus a, the magnitude of t is equal to e power minus a into t for t is greater than 0. Okay, my dear students. And it's equal to 1 for t is equal to 0. And is equal to e power for negative values is a minus already there, minus into minus is a plus, e power at for t less than 0. Understood, my students? What is the e power minus a, the magnitude of t means you can take it as 3 equations at the t is greater than 0, is equal to 0 and the less than 0. Greater than 0 means the t is a positive. Positive e power minus a, and I am taking it the positive value e power minus a t. Negative exponential. And if t is equal to 0, the value is a 1. And t is equal to less than the 0, minus a, and the t is a minus value, so minus into minus becomes of a plus value, e power 80. The 3 different functions. So now the integration is also divided as 3 parts, minus infinite to 0 means just below the 0, my dear students. 0 minus e power, what is the negative value, sir? The x of t, e power 80. E power 80 into e power minus j omega t dt. So this function is totally multiplied with plus another integral 0 minus and 0 plus, just below the 0 and just above the 0, nothing but equal to the 0 only, my dear students. And what is the e power 80? E power minus a magnitude of t is a 1. 1 into e power minus j omega t dt. Okay, my dear students. Plus another integral is a 0 plus, just above the 0. It is a greater than means just above the 0. Less than means just below the 0. Okay, 0 minus 0 plus to infinite. What is the e power minus a magnitude of t? E power minus a into t e power minus j omega t dt. Understood, my dear friends? So I split the 3 parts of when I am assuming the e power minus a magnitude of t is equal to, now I can substitute the integral minus infinite to, let it is a 0 minus is a 0 only. 0. Bases are same, e power. Take the my t as a common. A minus j omega into dt plus, here it is becomes of e power zero plus minus e power minus 0 minus, my dear students, 0 minus, okay, plus, and this value is a integral zero plus to infinite. It becomes of the base is the same. Take the minus t is a common, a plus j omega into dt. Okay, if we have any little bit confusion, you write this is also the integral form only. Integral 0 plus, not the 0 plus, 0 minus, minus 0 minus 0 plus e power minus j omega t dt. Okay, is equal to, what is the integral of e power x? E power a minus j omega into t with the limitations of, and we have to get the denominator also, whole divided by a minus j omega with 0 and minus infinite plus, what is the e power minus j omega t with the minus j omega 0 minus and 0 plus, minus plus, and this one is a e power minus a plus j omega into t whole divided by minus a plus j omega. Okay, with the limitations of 0 plus and infinite. Now I can substitute the upper limit and the lower limits. When I am substituting the upper limit is there 1, lower limit is a 0. That is equal to, for the first one, 1 by a minus j omega plus, and for here 0 plus e power 0 is a 1, and again the e power 0, the minus 1 becomes of 0. 1 minus 1 by j omega. So 0 by minus j omega plus, and here upper limit is a infinite, is a 0, lower limit is a 0, the value is 1, minus and minus get cancelled, 1 by a plus j omega. 1 by a plus j omega. So 0 by anything is a 0 here. So first term 1 by a minus j omega, and second term is 1 by a plus j omega. 1 by a square a plus b into a minus b square minus b square. B square is b is j omega whole square minus square. So is equal to 1 by a square. What is a j square is nothing but minus 1. So plus omega square. X of omega is equal to. Now the Fourier transformation of e power minus a magnitude of t. E power minus a the magnitude of t is 1 by a square plus omega square. If it is a normal frequency, a square plus 2 pi f. You see here, the value we got a square plus 2 pi f whole square. That is for the e power minus a the magnitude of t only. Here they wrote directly the equations. So without knowing the Fourier transformation of e power minus a the magnitude of t, it is somewhat difficult to find out the signum function. So what is the x of omega? I got 1 by a square plus omega square. Means e power minus a the magnitude of t. What is the Fourier transformation? 1 by a square plus omega square. Following my dear students. And its magnitude you can calculate. See, actually it is also the wrong. I am taking the LCM means you have to get the numerator also. What is the numerator here? A plus j omega. A plus j omega plus a minus j omega. If you take the LCM is a minus b into a plus b minus students. Minus get cancelled, plus and minus. Now get the 2a into, okay, here also the 2a by a square plus omega square. You can plot the phase plot and the magnitude plot also for this one. Okay, my dear students. And how we got e power minus at a plus j omega. But what is the e power minus at? E power plus at. Plus at means definitely it is a 1 by a minus j omega only. 1 by a minus j omega, my dear students. Now let us see that also. So before going to that, have to see the Fourier transformation of the signum function. Fourier transformation of the signum function. Okay. So with e power minus at magnitude of t and the signum of t is equal to signum of t, I am taking the function. Okay. You see that. Remember this is the x of omega is equal to 2a by a square plus omega square for e power minus at the Fourier transformation. Now here I am taking the e power minus a the magnitude of t the signum of t. So signum of t is equal to 1 for t is greater than 0, my dear students. Minus 1 for t is less than the 0. We know is one of the standard function, the Fourier transformations. And when I am taking this as a total signal function, total as a signal, e power minus a, the magnitude of t, signum of t. So totally as a one function, as x of t, let us just say x of t. Okay, my dear students. And this signum of t and this function e power minus at having the greater than 0 and the less than the 0 and equal to, we got that is also 0 after applying the Fourier transformation of this function. Following, my dear students, e power minus at, what is the e power minus a, the magnitude of t, for t is greater than 0. For t is greater than 0, the e power minus at. And similarly, the e power minus a, the magnitude of t, for t is less than 0, it becomes of e power plus at, my dear students, plus at. So for greater than 0, 1 is multiplied with the e power minus at because it is a value is a 1. So following these two functions, x of omega is equal to find out the Fourier transformation of this function, x of omega is equal to integral minus infinite to infinite x of t e power minus j omega t dt. Okay. And comparing these two functions here, for greater than 0, signum function is 1 here, e power minus a magnitude of t is e power minus at into 1, my dear students. E power minus at into 1. So what is that values greater than? So before I am taking the less than, minus infinite to 0, infinite to 0, minus just 0, 0 minus. For negative values see here, less than the 0, e power minus a, the magnitude of t is e power at, e power at, and what is the signum function? Minus 1, e power at into minus 1, and this total x of t into e power minus j omega t dt. Understand, my dear friends? Plus, so x of t, I take it as e power minus a, the magnitude of t, signum of t. E power minus a, the magnitude of t for less than 0, the value is e power plus at. And here the signum function is a minus 1. So I'm multiplying these two functions. And the second one is the 0 plus just below to the infinite. What is the signum function here? 1. And what is the e power minus a, the magnitude of t? E power minus at. So e power minus at into 1 e power minus j omega t dt. Okay, we got the two integral values and the two terms. The first, if I am taking this minus e power at e power minus j omega t dt as of the integral minus infinite to 0 minus. For the second integral, 0 plus to infinite e power a minus at e power minus j omega t dt. So bases are same, you can add the powers. So minus, I'm directly applying the integration also. After adding this, t into a minus j omega whole divided by a minus j omega with the limitations of infinite minus infinite to 0 minus plus what is the base here? The same. Take the minus as a common. A plus j omega into t whole divided by the t coefficient is minus a plus j omega with the 0 plus and upper limit is infinite. That is equal to, when I substitute the upper limit here, the first term, so e power 0. E power 0 means is a 1. E power infinite becomes 0 whole divided by a minus j omega plus, now here the upper limit is infinite becomes 0 minus the lower limit is 0 becomes 1 minus of a plus j omega. Okay, my dear students. Now you can simplify this function as minus 1 by a minus j omega minus into minus plus, my dear students, here 1 by a plus j omega. Take the LCM as a minus b into a plus b, a square minus j square omega square, j square is a plus minus 1 becomes of a square by omega square. And now here the LCM is minus of a plus j omega, a plus j omega plus a minus j omega minus in the numerator. Now see, here the minus a plus a get cancelled, minus j omega and minus j omega. So minus 2j omega whole divided by a square plus omega square. A square plus omega square. Following. So it becomes of minus 2j omega. Minus 2j omega means omega you can write as 2 pi f. 2 pi f means minus 4j pi f. See here, minus j 4 pi f, and numerator, denominator you can see a square plus 2 pi f whole square. A square plus 2 pi f whole square. That is a Fourier transformation of the signal. Following, my dear students. Now only individually you can take it as a signum function. Individually as a signum function. Signum of t. To find the signum of t, the function, I already told you have to know what is a Fourier transformation of the step function and Fourier transformation of the 1 also. The Fourier transformation of 1. Why? The signum function is in the form of a step function is 2 into mu of t minus 1. 2 into mu of t minus 1, my dear students. Mu of t saying that the mu of t 1 by j omega. We already seen that 1 by the j omega we got, or it is a 1 by 2 by j omega. So it is very important to find out the Fourier transformation of 1 and the Fourier transformation of the mu of t. We already seen the Fourier transformation of the delta function is a 1. And what is the Fourier transformation of 1 also? Fourier transformation of 1 also, my dear students. There is a indirect method and the direct method to find out the Fourier transformation of the signum function. Fourier transformation of the signum function. Until we have to find out only this function only, my dear students. That is minus 2j omega by a square plus omega square. Remember this value also. So I will write it as in the another way. You go here. We already seen the step function is 1 by j omega. Remember this. And e power minus a, the magnitude of t, signum of t, Fourier transformation is minus j minus 2j omega by a square plus omega square. A square plus omega square, my dear students. And the Fourier transformation of e power minus at mu of t also we seen is 1 by a square plus omega square. And we already seen these also, the Fourier transformation of delta of t is 1. And Fourier transformation of mu of t, Fourier transformation of mu of t, we got, see this is a mu of t, 1 by j omega. This is from, by the definition of the Fourier transformation we derive. Another way is also the mu of t is the Fourier transformation is a different minded field. It's not, it's the 1 by j omega in other manner. So let's you see that also. And to find out the Fourier transformation of the signum function, signum of t, the Fourier transformation, what is the signum of t? 2 into mu of t minus 1, my dear students. So Fourier transformation. So you know that 2 into mu of t, the Fourier transformation is 2 by j omega, and also you have to find out the Fourier transformation of 1 to get the total signum function. Okay, how it is the Fourier transformation of 2 into mu of t. 2 into, what is the Fourier transformation of mu of t? 1 by j omega. 1 by j omega, my dear students. One by j omega. And minus 1, the Fourier transformation of 1 also you have to find out. 1 also you have to find out. Then we'll get the finally the signum of t, the Fourier transformation. Signum of t, the Fourier transformation. Means a minus of the Fourier transformation of the 1 also. So what is the Fourier transformation of 1? Let us find out that one. The Fourier transformation of given x of t is equal to 1. Fourier transformation of the signal one. Okay, it is a direct method. You are not it is not possible to find out by using the direct by the definition of the Fourier transformation. You go for the indirect method to find the Fourier transformation of the signal 1. We know the delta of t. What is the Fourier transformation of delta of t is 1. But don't say the Fourier transformation of 1 is a delta of t. It is the inverse Fourier transformation of 1 is a delta of t. Means if I am assuming the x of t is equal to delta of t. Okay. And what is the Fourier transformation of x of t? Fourier transformation of x of t is x of omega. Okay. Fourier transformation of x of t is x of omega. And what is the Fourier transformation of delta of t? Is 1. So it is a pairs. Delta of t is a Fourier transformation pair of 1. So x of omega is equal to 1, my dear students now. For the signal of x of t is equal to delta t, x of omega is equal to 1 only. Otherwise, you can, without confusion, x of t is equal to delta of t, x of omega is equal to 1. Okay. Now we got one idea. That is x of omega is equal to 1. Means, according to the duality property, so very important, my dear students here. According to the duality property, it states that x of t, the capital X of t, the Fourier transformation 2 pi into small x of omega, x of minus omega. How we can prove this is the duality property? First, by taking the x of omega is equal to integral minus infinite to infinite x of t power minus j omega d dt. So interchange the omega and the t. Then the next step, replace the omega by minus omega. So finally, we'll get the x of t as 2 pi into x of minus omega. Okay. Here the signal is x of t is equal to 1, my dear students. Here the signal x of t is of 1. The Fourier transformation is 2 pi of, what is the x of omega? X of minus omega. X of t is equal to, it is a 2 pi into x of minus omega only. Let us write it without confusion. Here the x of t is equal to 1. And the Fourier transformation is 2 pi into x of minus omega. X of omega minus omega will be the delta of omega. Okay. So 1 with the Fourier transformation, it becomes of 2 pi x of omega. It is a minus delta of omega. Minus delta of omega. Here we know that delta of omega will be an even function. Delta of omega will be an even function. Delta of minus omega is also becomes of delta of omega. Since the impulse function, since it is an impulse function, having only the value is 1. Having only the value is 1 at t is equal to 0, or if it is a shifted, the value is t minus 1 also will get the only 1 value. T minus 2 is also will get the only 1 value. So the delta function, impulse function is even function. Impulse function is even function. So delta of minus omega becomes delta of omega. Okay, delta of omega. So now the Fourier transformation becomes 2 pi into delta of omega. The Fourier transformation is 2 pi into delta of omega. Okay, my dear students. So you have to remember this one. The Fourier transformation of 1 is 2 pi delta omega. The Fourier transformation of delta of t is 1. Don't confuse here. Why I wrote it's x of minus omega is a delta of omega, x of t is equal to 1. Okay. According to the duality property, you can interchange these functions. Interchange the function. Actually, the x of omega here, the t is a omega, my dear students. X of t is a delta function. Okay. As a duality property saying that x of omega is equal to integral minus infinite to infinite x of t e power minus j omega t dt. What we are saying that is according to the duality property, interchanging of omega as t. Omega as t. See, x of omega now it becomes of x of t, and that x of t I take it as a 1. Okay, is equal to integral minus infinite to infinite is x of t as a delta of t. Actually, now it becomes of t changes as omega, delta of omega. E power minus j omega t d omega. You see now, the x of t signal becomes of delta omega, and x of t I'm taking is a 1. Okay, the Fourier transformation of 1 is a 2 pi into the x of omega. According to the duality property, actually this is the x of omega and the x of t. What is the x of t here? Delta of t. X of omega is equal to 1. So I interchange it according to the duality property. So I take the x of t as a 1 here, and x of t as delta of nothing but delta of minus omega. So according to the, since not the according, sorry, since the impulse function is an even function, delta of minus omega is equal to delta of omega, then the Fourier transformation of 1, the Fourier transformation of 1 is a 2 pi delta of omega. The Fourier transformation is 2 pi delta of omega. Remember this one. Okay. Here, now we got 1 the Fourier transformation. 1 the Fourier transformation is 2 pi delta of omega. We got the mu of t as 1 by 2 pi, and the Fourier transformation is 2 pi into delta of omega. Now we go for to find out the signum function. So these are all we find it because of the signum function Fourier transformation. Let the x of t is equal to signum function, signum of t. Find the Fourier transformation. Find the Fourier transformation of the signal x of t as a signum function. So x of t is equal to, we know the signum function, signum of t, that is equal to signum of t can be written as 2 into mu of t minus 1. If I take the derivative of d by dt of x of t, apply the derivative on both sides, 2 into d by dt of mu of t minus 1 is a derivative of a constant is a 0, my dear students. Okay. Then after, the Fourier transformation of d by dt of x of t is equal to 2 into the Fourier transformation of d by dt of mu of t. What is the d by dt of mu of t? Nothing but impulse function, my dear students. I already told for impulse, apply the integral for the impulse, you'll get the step, unit step. For step, we can apply the integral, we'll get the ramp. Okay, ramp derivative is a step derivative is impulse. Step derivative is impulse, reverse operation. Apply the integral for the impulse, you'll get the step. Apply the integral for the step, you'll get the ramp. Apply the derivative with the ramp, you'll get the step. Apply the derivative to the step, you'll get the impulse. So 2 into the Fourier transformation of d by dt of mu of t is a delta of t. Fourier transformation of d by dt of mu of t. The d by dt of mu of t is a step function, not the step, impulse function. We know the Fourier transformation of delta function is a 1, 2 into 1. What is the derivative of any signal derivative? The Fourier transformation of the derivative functions. Okay, time differentiation in time r. Okay, j omega into x of omega. Integration is x of omega by the j omega into x of omega. Okay, the Fourier transformation of derivative of the x of t. Following my students, derivative of any signal is j omega into x of omega. So you need the x of omega. X of omega is equal to 2 by j omega. Means the signum function, the Fourier transformation is 2 by j omega only. 2 by the j omega. Understood? The signum function, signum of t, the Fourier transformation is 2 by j omega. Understood, my dear students? But now I said that the mu of t here, the Fourier transformation, it wrote the minus Fourier transformation of 1. Whenever if I am taking the signum function, you can find out the Fourier transformation of these functions. 1 with the 2 pi delta of omega, and it is a 2 by j omega only. There is no any the Fourier transformation. Here the 2 by j omega only we got. This we can use to find out the step function by using the signum function. Okay, the Fourier transformation of the step function by using the signum function here. Okay, let us see. The t into mu of t into mu of t minus 1 is equal to signum of t. Okay, my dear students. So what is a mu of t here? Mu of t, I will explain. It is in the other way. So signum function, signum of t is equal to 2 into mu of t minus 1. Okay. Mu of 2 into mu of t is equal to 2 into mu of t is equal to signum of t plus 1. And mu of t is equal to 1 by 2 into signum of t plus 1. Now apply the Fourier transformation. The Fourier transformation of mu of t is equal to 1 by 2, the Fourier transformation of signum function, signum of t, plus the Fourier transformation of 1. Okay, my dear students? That is equal to 1 by 2. What is the Fourier transformation of signum function? We got a 2 by j omega. 2 by j omega plus, what is the Fourier transformation of 1? We got 2 into 2 pi delta of omega. Okay. Now the 2 is 1 by 2 is multiplied by the two functions. The 2 get cancelled. So Fourier transformation of mu of t is equal to pi into delta of omega plus 1 by j omega, my dear students. The Fourier transformation of mu of t. Okay, pi into delta of omega. So now the mu of t, the Fourier transformation is a different, without using the formula, using the signum function, it is a different. It is a pi into delta of omega plus 1 by j omega. It's another method. By using signum function. Okay, my dear students. mu of t is equal to pi into delta of omega plus 1 by j omega. So today we learn Fourier transformation of delta of t, the Fourier transformation of mu of t, the Fourier transformation of signum of t, and the Fourier transformation of using the signum of t. And another also you can find the e power minus a, the magnitude of t, signum of t. The Fourier transformation is minus 2j omega whole divided by a square plus omega square. Okay, my dear students. Now I can see the remaining examples of the Fourier transformation in the next class, my dear students. Any doubts? Please rise. Okay. Thank you.